With that, it's my pleasure to introduce sort of our guest speaker. We have this tradition at JumpDev of inviting someone external to Jump to kind of talk about the cool optimization stuff they're doing. Today we have Bethany Nicholson from Sandia National Labs, from what I call informally the Pyomo team, talking to us about Pyomo and some of the cool things they're doing. So looking forward to what she has to share with us today. And with that, let's welcome Beth.
Thanks, Josh, and thanks to all the JumpDev organizers for inviting us to be here today. I probably have the dubious distinction of being the only person in the room who's never written a jump model, so forgive me for that. So the first thing I want to say is when we were invited to come here and speak today, the entire Pyomo development team was really excited about the opportunity. And so we brainstormed all of the cool things we could talk about, and as a result, there's probably way too much content for me to cover today. So as we get near the end, you'll see me probably speed up, but I'm happy to have, additional conversations after the talk. I just want to recognize the whole Pyomo team for contributing content to this, in particular, John Cirola and Emma Johnson. So, I guess let me start by answering the question of what is Pyomo. This will sound very familiar to kind of the overview that Miles gave yesterday, but Pyomo is very similar to JUMP. We are an algebraic modeling language written in Python, and we focus on being able to formulate and solve structured optimization problems. So everything is written in native Python. We have a set of objects, classes, and methods for expressing different types of optimization problems. And then we have a growing collection of utilities and infrastructure for manipulating optimization problems in neat ways. We are also now the base of many other domain-specific optimization modeling packages, and that's where a lot of the new development and funding to support Pyomo comes from these days. And then I guess the last thing I have to mention is we also have a really cool origami bird. I'm a bit biased, but I think this is my favorite software logo of all time. So I just wanted to give a really brief history of Pyomo. It was first released in 2008 as the Cooper software library. We rebranded as Pyomo around 2011 and moved our development to GitHub in mid-2016. Since then, we've seen pretty steady growth in usage and popularity. According to GitHub, there are around 1,800 repositories, 174 packages that depend on Pyomo. In the last year, we've released 5 releases, around 239 pull requests from around 30 developers. So you can see our plot of GitHub stars over time, and if we project that into the future, we should hit about 1 million stars in maybe another 2,000 years, so we'll get there eventually. This is one of our favorite kind of high-level overview slides, kind of showing how Pyomo is structured. So this maps pretty cleanly to kind of where the code lives in different repositories. So everything in this center box is essentially things that live in the main Pyomo repository. We have, of course, things like core optimization and modeling objects, things you would expect to find in any algebraic modeling language. And then a number of solver interfaces to your favorite optimization solver. I think some of the features that make Pyomo special over maybe more historic algebraic modeling languages is that we include different types of modeling extensions for specific classes of problems. So you'll see a lot of overlap with some of the Julia and jump extensions that we've talked about yesterday and this morning. And then the idea of model transformations for taking these high-level constructs and transforming them into something that an off-the-shelf optimization solver can understand and handle. in addition, because we're in Python, we also have a lot of flexibility in what we can do with scripting, and so we've been using that to develop a number of different meta solvers for solving different classes of problems. Some of those can take advantage of some of these high-level structures directly, which is pretty cool. Outside of the main Pyomo repo, there are a number of external extensions that build on Pyomo in different ways. I won't have time to go into those today. And then I mentioned we spend a lot of time right now working on different derived domain-specific modeling languages. So I have some of those listed, which correspond to some of the funded projects that has been supporting Pyomo development over the last, let's say, 8 to 10 years. So, to answer the question on everyone's mind, why am I here if I'm not a JUMP developer? Well, I think the point of me being here is really to exchange some ideas with the same community that cares about software for optimization. And so I'm hoping to share some insight from the Pyomo perspective of different design paradigms we think we've got right over the years. Some lessons we've learned, things that haven't stood the test of time and have been refactored, and then give you a flavor of some of the new features and packages and kind of what's coming next for Pyomo. And again, there I think you'll see a lot of overlap with some of the things we've talked about since we've been here. Okay, so I want to start with some of the motivating design principles for Pyomo. And the first thing is that we really wanted to be able to express high-level model structure. We want to express structures and expressions that match our understanding of the system. We want to be able to formulate large models with a concise syntax, and we wanted to support things like model composition, high-level logic, dynamics, multi-level optimization, things like that. We also wanted to be able to explore new algorithms and approaches. And under that category, this means things like having really careful strategies for managing the translation from what the user said and what makes sense from a user perspective of how you formulate and think about your optimization problem compared to what the solver understands and is able to solve. We also wanted to be able to more quickly and easily explore ideas and algorithms around decomposition, relaxations, model reformulations, and iterative analysis algorithms. So you can think of meta solvers that require multiple solves, maybe from different types of solvers. And then finally, we wanted to have a platform where we could build domain-specific optimization libraries. So again, this is reflected in a lot of the projects currently funding Pyomo, but the ultimate idea is to make it easier for researchers to make their innovations and algorithmic advances available to the community and make it easier to implement very general packages that implement their latest and greatest algorithms and then be able to distribute those to the community so they don't just die or get stuck with the one paper where that method was described, right? In terms of domain-specific libraries, we have things for electric grid, process model libraries, and things like asset scheduling. Okay, so given these motivating design principles, one of the, key things that has come out of these principles is the idea of capturing structure in our optimization models. From the Pyomo perspective, we do this using a concept called blocks. So every Pyomo model is a block. It can also contain blocks. And a block is just a collection of modeling components. So you can think of like variables, constraints, objectives, params. These all live within a block. The cool thing is that you can have blocks within blocks. So this leads to a really nice hierarchical structure for Pyomo models that can capture some really interesting problems in interesting ways. These blocks can be solved independently from the rest of the model, which is really helpful for debugging and initialization. We can turn on and off different portions of the model really easily. And then this also ends up being really useful for namespacing. So especially if you're building up a model library where you want to be able to compose models, you don't want to worry about name conflicts. And so having all of your submodel components on a specific block means you don't really have to worry about, what the person developing the model over there that you want to interface to named anything, because they're all kind of separate namespaces. And so this concept of hierarchical modeling has really become core to Pyomo. As I mentioned, blocks facilitate model composition. So in different contexts, you can think of process modeling, where you may decompose your model into different unit models. And within this unit model, you might have control volumes and state blocks and ports that interface to other unit models. In the context of grid modeling, you can think about having blocks that contain individual instances of an optimal power flow problem that can then be linked together in time, or doing contingency analysis. And then you can also think of blocks in the context of stochastic programming, where you're trying to link together different realization scenarios of some uncertainty. This concept is useful for model composition, but it's also really useful for thinking about decomposition as well, because again, we're capturing some of this high-level structure, which then naturally leads to breaking points of where you can decompose your model as a result. So this idea of thinking about kind of how to exploit the structure for model decomposition caused us to go back to the drawing board in a sense and really analyze the question of what is a model. What do we mean when we say we have an optimization model? And it's convenient to think of a model, a solvable model, as everything that's contained below a single block in this block hierarchy that I have talked about. And that every subblock needs to be self-contained, meaning that it has to contain all variables and constraints that are associated with that subblock. So on the surface level, this makes intuitive sense. However, when you start getting into more complex things like transformations and some of these high-level modeling constructs, this conception of what a model is can really start breaking down. So if we look at trying to incorporate things like disjunctive programming, maybe we have separate blocks representing individual disjunctions, and then some kind of logical expression or constraint at the next level up in the block hierarchy. Well, I can't send this to an optimization solver. So the Pyomo thing to do is to apply a transformation. Maybe we're doing a big M transformation here, which now gets generated and added to its own block. But now we have a problem, because these indicator variables for each of the individual disjunctions were defined on these disjunct blocks, and so they're now separate from here, and the concept of a solvable model containing all of the variables that it needs to solve a particular block really starts breaking down. So the block hierarchy in Pyomo has really influenced our understanding of what's a model, and we had to go back to the drawing board and really refine our definition of a model. And so now we've settled on this definition, which is that a model is the collection of all active components reachable by descending through active blocks, starting from a reference block. And so in Pyomo, we make the distinction between activatable components and non-activatable components. An active component is a block, a constraint, disjunct suffix, and very importantly, things like param, set, and var, these are not active components. And so these aren't used to distinguish what we mean when we say a model. Our model is really defined by the set of active constraints accessible through active blocks. So having this kind of updated definition allows us to address a lot of edge cases that have appeared over the years in Pyomo models for being able to consistently handle kind of the scoping of what we mean when we say a model. Another key observation that we've had through all of this is that, well, Pyomo models are just trees. The models themselves are trees, as we've seen through this block hierarchy. But then under the hood, all of the Pyomo expressions are also trees. And so by recognizing that this is really the fundamental data structure behind Pyomo, even for things like linear expressions, this means that our representations can be a little slower than custom representations for specialized structures, but it also makes model manipulation much easier because we have fewer special cases to worry about, because we don't have a lot of different types of representations under the hood that are exploiting certain special structures. This also means that the fundamental operation on a Pyomo model is just an expression walker. So if we want to focus on making things easy to extend, easy to combine different extensions, things like that, it allows us to really focus all of our effort on making those expression walkers efficient, easy to write and extend. And so that's where quite a bit of our development effort has been in the core of Pyomo over the last few years. So we've shifted to leveraging multiple dispatch for kind of walking our expression trees. So this is an idea that we actually got from JUMP and has allowed us to improve things quite a bit on the Pyomo side. And then we've been able to use multiple dispatch in a number of the writers and expression walkers that we have within Pyomo. We're also continuing to incorporate some of these ideas into some of our other walkers and writers. Okay, so let's see how I'm doing on time. So we've talked about kind of this high-level block structure as one way of capturing optimization model structure, but there's another type of structure that we really care about and think about a lot in Pyomo. And so to introduce that, I'm going to put this up there and ask, what do these all have in common? And the answer is that they are all different ways of formulating an absolute value function. So if we mean A equals the absolute value of x minus 3, why do we have all of these different formulations? Why don't we just write absolute value directly in our optimization problem? And it's this question that has inspired a lot of the development and kind of design that's gone into Pyomo around distinguishing between what do we mean when we talk about an optimization model, and what do we mean when we talk about an optimization formulation. So from our perspective, again, we're asking ourselves, well, what is an optimization model? We ask ourselves this a lot from different contexts. And from our perspective, an optimization model is a general representation of a class of optimization problems. It should be data independent, and it should really capture the modeler's understanding of a specific class of optimization problems. And we distinguish that from a formulation because, from our perspective, a formulation is really just how we communicate that optimization model in a tractable way to a particular optimization solver. And so we do everything in our power to allow modelers and users to think about their problem in the context of an optimization model and a syntax and kind of high-level representation that makes the most sense to them, and defer this problem of communicating with the solver with a particular formulation till the very end. So if we look at kind of the standard algebraic modeling language workflow, we might start with combining some kind of model with data to create an instance, taking that instance and communicating it to an optimization solver, and then getting an answer. The problem with, say, the old way of thinking for algebraic modeling languages, so circa 2008, before Pyomo and JMP were on the scene, the real challenge comes in these two steps at the end. So this translation between a model instance to an optimization solver really requires the user, the interface, to know what the solver expects. So it requires the user to be able to speak solver. And that translation is really solver specific. So you needed to ask yourself questions like, well, is this a linear solver? Do I need to linearize everything? Does it need to be continuous? Can it have logical structures? Things like that. And the problem is that if you didn't get this translation right, there were issues with whether you'd even be able to get a solution out of your model or your formulation. So for difficult instances, in order to even get an answer, you need to be thinking about things like scaling and having things well structured and sparse and kind of tight bounds or relaxations on things. So Pyomo has taken this concept of a transformation to take care of these last two steps for you. And it's for allowing users to represent their models in the most intuitive, user-friendly form, and then provide tractable reformulations that can be automatically applied to allow you to do this step of translating your model to the optimization solver. So we believe transformations enable much more intuitive modeling. Our workflow looks something like this instead of kind of everything staying in the original modeling space. And this design really allows us to separate the model expression from how we intend to solve it. So this is what allows us to support different types of nonlinear modeling constructs, so GDP, DAE, things like that. It allows us to defer decisions that improve tractability until we're ready to actually send the model to a solver. And it allows us to explore different reformulations or representations for some of these high-level modeling constructs. I mentioned earlier that one of the other cool things this allows us to do is write meta-solvers that operate on some of these high-level structures. And then I think the last, maybe obvious benefit is that this allows us to reduce the mechanical error due to manually applying some of these different reformulation tricks. So transformations is something that we use quite a bit. We have a growing library of different Pyomo transformations for different classes of problems. You can see some of those there. But overall, we've been really happy with this design choice. Okay. I'm running a little short on time. I want to leave lots of time for questions, so I'll skip through the next few things pretty quickly. With this slide, I just wanted to point out that over the last couple of years, we've really been taking a look at our solver interfaces and redesigning those in a number of ways. So trying to think about concepts outside of just the kind of file-based solver interfaces that we've historically had in Pyomo. So we've been playing around with ideas of kind of direct and persistent solver interfaces, and we're making some improvements and extensions on that front. We've also been thinking more about model compilation. So this is showing an example of some work we've done recently with rewriting our NL writer. So this is how we communicate nonlinear optimization problems to nonlinear solvers. We go through the ample solver library to do all of our AD, which requires outputting our Pyomo model into an NL file format. And so we've made some significant improvements to that over the last year or two. Some important new features is that we now have a linear pre-solve built into our NL writer that allows us to do variable aggregation. So this is showing an example of solving a DAE optimal control problem with and without that pre-solve. And we've found that for some problems that can make a really big difference. And then we're also able to do some more efficient model scaling with some of the changes we've made in that NL writer. We've also been thinking more about compiled representations. So I mentioned at the start that all Pyomo models are expression trees and that we don't have specialized representations. But because we've taken that kind of generic look and have that generic infrastructure in place, we now also have the flexibility to extract out some of these special structures from those expression trees and using the existing infrastructure that's in Pyomo. So this has allowed us to start exploring compiled representations like a linear standard form, leveraging some other packages in Python like SciPy and NumPy. And we're seeing that this allows us to represent some really large-scale problems really efficiently within Pyomo. The last thing I want to mention on kind of design paradigms is that we've started to explore some new algebraic modeling language ideas that have a stronger focus on performance. And so we've been kind of co-developing a couple of other ideas in packages external to Pyomo. So things like Coke, which is implemented in C++, Poke, which is kind of a Python interface to Coke, Pyomo Coke, which kind of brings things together and starts looking at optimization models that are kind of defined in Pyomo but have a lot of the underlying numerics and computation still on the C++ side, which allows some interesting performance improvements and implications. And then Smoke, which is starting to look at compact expressions, compiled expressions, representations, and things like that. So kind of with some of these other AML ideas we've been exploring, it's really allowing us to explore some of the trade-offs between model expressibility, performance, and ease of implementation, whether you're trying to implement things in Pyomo or C++ or some hybrid of the two. The last couple things, these are some of the Pyomo extensions that are currently under active development. So you'll see a lot of overlap, again, with some of the extensions that have been talked about here for the Julia jump side. I don't have time to go into any of these. I have a couple backup slides if you want to ask me about them after I'm done. But these are, some of the newest, latest, and greatest things we've been working on. So my next two things I wanted to mention, just inspired by some of the discussion yesterday. So there was some talk yesterday about like parameterized optimization problems and the idea of having parameters in your model that where you could swap out the value easily without rebuilding the entire model. Pyomo has had this concept since its inception, so I just wanted to point it out here. We've had a lot of, there's actually a lot built into supporting params and data components within Pyomo that goes on behind the scenes to do this efficiently. So having the concept of a mutable param to indicate that the value may change and telling us that this data needs to be preserved in the expression tree until the last second when the model is sent to a solver. That makes it very easy to update that parameter without having to rebuild everything. And then we have some interesting infrastructure for indexed parameters around setting a default value, which is really helpful if you have sparse data, for example. Units was another thing that was mentioned in the kind of what's next for JUMP talk. We've had units handling for the last couple years. This turned out to be a pretty big challenge, honestly, to get to work right. I mean, units touch basically everything in the expression tree, and so this actually required quite a few changes to the core of Pyomo to support effectively, and so this is kind of the API that we've settled on. We use the Pint Python package to do all of our units. And then we have some nice utilities in Pyomo for asserting consistent units and identifying sets of constraints and objective functions that may have inconsistent units. So this is what it looks like. You can assign units to things like variables, parameters, and external functions. Okay, so let me wrap up. Over the years, we've learned quite a few things from JUMP. I would say multiple dispatch is one of the big things. We've also learned to have to focus and think more about kind of direct memory solver interfaces and the benefits that those can have. We have some interesting ideas around templatization and abstract expression trees that have kind of come from JUMP and been cross-pollinated with some of the things we've been thinking about. And then kind of the last thing I wanted to mention was the idea of having a consistent dual convention in the modeling language. Don't take that for granted. It turns out if you rely on getting your dual convention from the solvers, it causes all kinds of headaches because those can be inconsistent. So I have a couple notes on kind of where we're going next. We've been slowly making some performance improvements over the last few releases. I'll say maybe the most important thing we've been thinking about is, it ties back a bit to Josh's talk this morning, is the idea of having template-aware writers or templatized models where you're not expanding everything and you can exploit that templated structure. We have some ideas around how to do that in the Pyomo side that we're currently working on. So thank you for your attention, and I'm happy to take any questions.
A great talk. Thank you, Bethany. Questions from the audience? I see Miles' hand going right up.
Yeah, thanks a lot for the talk. I'm wondering how you think about deciding which transformations to apply, because you can, often there's a choice of which transformation. So how does Pyomo approach that?
So I guess our perspective is we don't worry too much about it. We just try and make it as easy as possible to experiment with. And so, you know, especially for problems that maybe are combining different extensions, we try and make it easy to mix and match and experiment and play around with them. I would say there's not really any built-in infrastructure for, I guess, automatically looping over all of the different options and in telling the user which is the best, but I mean, I suppose you could set up a script to do that pretty easily.
Do you use, is there a default transformation? Like if you write down an indicator constraint, and do you have to say, I want to transform this to big M if the solver doesn't support?
Yeah, so there are no default transformations.
Okay.
So if you use one of these high-level modeling constructs and you try and just send it to a solver, the solvers will complain that you're sending them an object that they don't know how to handle. So it is a very manual process. We rely on the users and the modelers to kind of know their model best and apply transformations to get the model from that high-level form to a form the solver will understand.
Okay, yeah, on jump we do have some defaults, but it's, we don't have a way to optimize the right choice of transformations.
Mm-hmm.
Other questions? Yep.
Very quick, you mentioned you've got these new solver interfaces at pyomo.contrib.solver. Where is that in the world?
Yeah, so we've exposed the world to a totally.
Sorry, I mean, I'm just literally. It's a link to something.
Oh, so Pyomo contrib is just a folder within the main Pyomo repository.
It's within the right.
Yeah,
Okay.
yeah. So if you have kind of, I think we released it maybe 2 releases ago.
Yeah, I just couldn't find it.
Oh, okay.
I just like to look at it. Okay.
Okay.
How do you choose what goes into the main repo and what goes in a separate package before?
Yeah, that's really hard. I would say we've kind of settled on the standard of including most things in the main Pyomo repository under this separate contrib umbrella for kind of new features that come in. So we use that within the repo to distinguish between things that are more kind of beta functionality versus things that are part of our core offering. I mean, there's pros and cons. Obviously, it makes our repository a lot bigger, but we find that given our very limited kind of development and maintenance time that we have, that's kind of the best approach rather than maintaining separate repositories and CI infrastructure for each of the different extensions that we care about and we want to, keep maintained.
I guess a follow-up, how long does your CI take to run?
So we spread our CI between GitHub Actions, and we have an internal Jenkins server where we run kind of the proprietary commercial solvers and models that can't be in the public repo. Our GitHub Actions spread across a number of different operating systems, Python versions. Each individual action maybe takes about 45 minutes to an hour. Jenkins also takes maybe a little over an hour.
Anything else? I have my own questions, but I'll probably just save it for the coffee break, so I have too many. Well, let's thank our speaker one more time.